So in previous weeks, we've been discussing differentiation and not so much focusing on how to derive, but more on how they could be used. And we talked about various ways in which it could be used, in particular, graphically. And that includes your things like whether it's increasing or decreasing, whether it's concave up or down, and more specific things like your stationary points and your inflection points. Now you do need to know that very well. If you have any trouble with that, then go back and look that over. Now for kinematics, we briefly last week, along with your vectors, spoke about the concepts of displacement, velocity and acceleration, and how they relate to each other, and how we use calculus for that. So I assume you know that at this point. If not, then go and look that over. But basically, the very simple version is the derivative of displacement with respect to time is velocity, and the derivative of velocity with respect to time is acceleration. So those are two main applications of derivatives that we've spoken about before. And today we'll hopefully finish that off by basically talking about general rates of change, followed by application of max-min problems. So what we probably want to consider, and this is very useful to your understanding, is what is a derivative? Paris, what's a derivative?
The gradient.
Graphically, yes. So for example, if I want to find dy dx, one way to think about it is it's the gradient. And at that point, that's true. That's one interpretation, and that is the graphical interpretation. But we want to kind of go more generally. So in more general terms, what is a gradient? What is a derivative?
The rate of change.
Good, it's a rate of change. The rate of change of what?
Of x.
No, actually. So it is a rate of change.
Of y, when x changes.
It's a rate of change of y as x changes. So basically, it's how the top part changes, and more specifically, it's the instantaneous rate of change. Of y as small changes are made in x. And that is basically what dy dx would represent. So as long as you understand that, and just to be clear, the reason why that is true comes down from the definition by first principle. We said it's the limit as h approaches 0 of f of x plus h minus f of x over h, which can be thought of as the change in the y-coordinate divided by the change in the x-coordinate. You can go back and look at what we talked about before with our, first principles, as delta x approaches 0, and this is simply written as dy dx, and that represents change in y over change in x, and therefore the quotient of that is the rate of change of y with respect to x. Is that clear?
Yeah.
Good. Well, if that's clear, then when we do rates of change questions, it's quite simple. You're simply just taking this interpretation and then using derivatives in it. So, for example, so let's take a look at this example. It says a circular oil stain of radius r and area A is spreading on water. Differentiate the area formula with respect to time to show that dA dt equals 2 pi r dr dt. All right, so let's do that first. What shape is our oil stain?
Circular.
Right, and so it says the area formula. So how do we work out the area of a circle?
Pi r squared.
Right. So we agree that it's a circle. So basically the area must equal pi r squared. Now the question asks us to show that dA dt equals 2 pi r dr dt. Firstly, are you confused with that, or is everything clear?
I'm gonna be confused.
Okay. Well, we want to show this thing, all right? We want to show that dA dt equals 2 pi r dr dt, all right? Now the thing is this. Is the area of the Orstein changing, yes or no?
Yes.
It is. Is the radius changing?
Yes.
Right. So is the area a constant?
No.
Is the radius a constant?
No.
Right. So what you really basically need to understand implicitly is, I mean, you don't need to write this out. I'm just kind of telling you, but if you're getting confused, then this is the sort of thing you need to understand. A is the area, but note that it is not constant and is changing, right? You agree with that, yes?
Mm.
So if A is changing, it changes as what happens?
As radius change.
It does, it does. But if we ignore the radius for the moment, like when you say it changes, like we're basically saying it's different at what? At different points of?
Mm.
If it's changing, then it's different at different points of what? It changes as time changes, right?
Oh, yeah.
So therefore, it should be able to be expressed as a function of t. Do you follow that reasoning?
Yeah.
Basically, because it is not constant, therefore it will change as, you know, as t changes, it will change. Clear with that?
Mm.
Good. All right. Well, r is the radius, but this is also not constant and it's also changing, right? So you would understand that r is also a function of t, which we'll call rt, and we'll call this at, all right? Now, to be clear, you don't need to write this out, but you need to sort of understand this, you know, whether you write it out or not, you need to understand that this is the case. What I mean by that is area is changing as a function of t. We don't know this function, but it's some function of t. And r, we don't know this function either, but it's some function of t. Does that make sense?
Yeah.
And the reason is because it changes. And so now the question is, what's dA dt? Because if you take a look, the question wants us to find dA dt, right? At the very start, we want to find dA dt.
Mm.
So we know a equals pi r squared, but if we derive a, then we would get dA dt, right? If we derive a with respect to t, we're going to get dA dt, correct?
Mm.
All right. But deriving a is like deriving pi r squared with respect to t. Does that make sense?
Yeah.
Because after all, a is pi r squared. Agreed? All right. Well, here's the thing. Like, if you end up having that, well, then basically what's going to happen is, well, pi is a constant, yes?
Yeah.
So can we take that out?
Yes.
Good. Now, is r a constant?
No.
Is it a function of t?
Yes.
Yeah, it is. Now, we don't know what that function of t is. It could be anything. It could be, you know, sine x, exponential, x squared. Like, it could be anything, but we just don't know, right?
Mm.
But we need to derive r squared with respect to t. So think of it as we are deriving, like think of it as we are deriving something squared, where this something, you know, is some function of t. Like some green thing, yeah?
Yeah.
And so we would therefore use the chain rule, right? That means it's pi times 2 times the green thing times the derivative of the green thing with respect to t. Does that make sense? Do you follow where the chain rule, you know, comes in here?
Yes.
Right. And this thing is just r. So let me replace the green thing with r, which is what it is. Recognizing again that r actually is a function of t, and it's not just a letter or a constant. And that's where you get your 2 pi r dr dt as required.
Yeah.
Do you understand what we've done there?
I think so.
Good. All right. So we haven't done the question. We've just done the first part. Basically, we've got the, we get the area because it's a circle. So area equals pi r squared. Because area equals pi r squared, then we need to derive it. To get dAdt, we need to derive it not with respect to r, but to derive it with respect to t is the question. So deriving it with respect to t, recognizing both a and r are functions of t themselves, is deriving the left-hand side is deriving the right-hand side. But deriving the right-hand side means you can take out the pi and then dr squared dt, which just means, you know, using the chain rule. So if I just write out the working again in a different way, potentially, you know, you could write a equals pi r squared, dA dt. Another way to think of the chain rule is to think of it like a sort of fraction. So it's dA dt, dA on the top, dt at the bottom, and we want to fit in something both in the top and bottom that are the same. We haven't really been introducing the chain rule this way, mostly, but it's the same idea. So dA dr, just derive this with respect to r, and that will be pi times 2r, right? Times dr dt, which is 2 pi r dr dt. So this is just another way to write out the working. All right?
Yeah.
Clear with that?
Mm-hmm.
Good. All right. So now let's answer question A. Question A says find the rate of increase of area as, you know, when r equals 40 centimeters, if the radius is increasing at 3 centimeters per second. All right. Do you understand what the question is asking you to do?
Yes.
Okay. What is it asking us to find?
dA dt.
Correct. The rate of increase of area. So it's basically saying find dA dt. Indeed, when?
When r equals to 40.
Good. And
dr dt equals to 3.
correct. Exactly. So if you understand what these things represent, like, you know, you understand what dA dt represents, dr dt represents, then yeah, we're just basically subbing in things in, except in the past, you might only be, you know, comfortable with subbing in r and a. We're now subbing in values for derivatives as well. Does that make sense?
Yeah.
Because the derivative represents a rate. Now, the only thing I would add, although you've already basically got the key concepts, is whenever you're subbing in values for example, dr dt, you said 3, I would just add that always think about whether it's positive or negative. So in this case, is it positive or negative 3?
Positive.
How do you know that?
Well, it's a positive 3.
How do you know it's not negative?
Can't I just assume that it's positive?
So put it this way, when would it be negative? So in this question, it is positive 3, but when is it negative? And I don't feel like you've fully thought about that yet. Think of what dRdt represents. What does dRdt represent?
The derivative of
Yes,
what?
it is the derivative of r with respect to t. But if you think about it sort of conceptually, what does it represent?
The radius.
Well, r is the radius, but not dRdt. Conceptually, what is dRdt? What's dRdt?
Instantaneous rate of change
Of
R as what's the other thing? T changes.
So it's basically the rate of change of r, right? As time goes on, right?
Yeah.
And what if it was negative? What would that mean? If the rate of change is positive, what does that mean? If the rate of change is negative, what does that mean? How do you measure rate of change?
You derive it.
Well, sure, but let's stay away from calculus because we're just talking very basic concepts here. Just in general, before calculus, how did you measure the change first? How do you measure the change? For example, it's delta y over delta x, right? Which is like y2 minus y1 over x2 minus x1, right?
Yeah.
So that's like your gradient before you do calculus, right?
Mm.
What if this was positive? What does that mean?
The gradient is positive.
And what if it's negative?
Gradient is negative.
True. So what does that mean about the thing? That the grade. So if you think of gradient as a rate of change, what does it mean about the y value?
It's negative.
No, not necessarily. And just think about it from a curve sketching point of view as well. What does it mean if the first derivative is positive? What does it mean if the second derivative is first derivative is negative?
If it's positive, it means it's increasing.
Yeah. And if it's negative?
Decreasing.
So in this question, why is it positive?
Because it's increasing.
Correct. So it is positive 3, but you need to pay attention to the fact that it's increasing rather than decreasing.
Okay.
So I think a lot of students, for example, in a different question where it says it's decreasing at 3 centimeters per second, they would still write 3 and not having considered the sign. And that would just, be wrong. Because whenever you're talking about a derivative, it's a rate of change. So not only do you need to consider the magnitude of that rate of change, but also highly important is to consider, what is the change? Is it going up or is it going down? And if it's increasing, that means it's positive. And if it's decreasing, that means it's negative. Is that clear?
Mm.
Now, the other thing probably not so important for this question, but you should form good habits, is to pay attention to units. So R is 40 what?
R is what?
40 centimeters.
Yeah.
And the RDT is 3 centimeters per second, which means if we are using these units, which are fine, what we're basically saying is that we're measuring our distances in centimeters and our time in seconds. Is that clear?
Yeah.
So, you know, you don't have to write all of these things out, but you do need to be considering them. So our distances using these are in centimeters and our time is measured in seconds, because other questions might need you to do conversions, right? They might say, you know, 2 meters long or something like that, in which case you might need to change to 200 if you're using, you know, meters, if you're using centimeters.
Yeah.
You have to decide what unit you're using. Once you've decided, as long as you're consistent, it doesn't matter. All right, so then we just basically go ahead and sub it in. So d a dt equals 2 pi r dr dt. We know that. Well, we know that r is 40, so times that. And dr dt is 3. And in this case, it would just be 240 pi. So the answer is 240 pi. But as I said before, pay attention to units. So this is area, right?
Yeah.
So what's the unit of area here?
cm squared.
Yeah, square centimeters. And it's a rate of change is dAdt. So 240 pi square centimeters per second.
Yeah.
Right. Clear with that?
Yeah.
Any questions?
No.
All right. So B, find, you know, the rate of increase when r equals 60 centimeters if the area is increasing at 10 square centimeters per second. So this is now our condition. We already have dAdt equals 2 pi r dr dt. Given that, then what do we do now? What is it really saying? Translate the question into maths for me. Find
dr dt when r equals to 60.
correct. I didn't write down the full question somehow. So of the radius.
Yeah.
So therefore it is I had read it, but I didn't write it. And so, yeah, that tells you it's dr dt when r equals 60 and implicitly centimeters and what?
And dAdt equals to 10.
Do you want to be more specific?
10 cm squared per second.
You want to be even more specific? It's a derivative. So what am I waiting for? It's a dAdt. So what am I waiting to hear?
Positive.
Exactly. I want to be I want you to explicitly make sure you've thought about it. Obviously, positive 10 is the same as 10, because when you say 10, it's assumed to be positive. But I want you to make it perfectly clear that you've considered, is it positive or negative, and made that decision.
Yeah.
As opposed to, well, I forgot about it, but I might have, it doesn't matter anyway, because this question is an increasing one. Does that make sense? All right, then it's just a question of subbing in numbers. So in other words, we know this is 10, like all the units match, so we don't need to really do anything. So 10 equals 2 times pi times 60 times dr dt. And you obviously just solve for dr dt. And you'll notice that it's 10 on 120 pi, which is going to be 1 over 12 pi centimeters per second. Are you clear with that?
Yeah.
Any questions at all with that?
No.
All right. So let's now do a very similar question. So this is a similar question. Now we've got this time a spherical bubble of radius r is shrinking so that its volume v is decreasing at a constant rate of 200 cubic centimeters per second. Show that dv dt equals 4 pi r squared dr dt. All right, so if we read the question, a spherical bubble of radius r is shrinking so that its volume is decreasing at a constant rate of 200 cubic centimeters per second. What has that told us? The first sentence.
It's a sphere.
Correct. As also, what else has it told us?
The radius and the volume are not constant.
True.
They are decreasing.
True. Is there a specific something equals something you can tell me?
The rate that the volume decrease is 200 cm cube per second.
Correct. That's the key thing. Now, can you translate that into maths then? Into maths sort of version? You've identified the right sort of phrase. And what is that mathematically? What does that mean? So it's a rate of change of volume, yes?
Yes.
So what is that? The rate of change of volume.
What do you mean? dv dx? dt?
dv dt, correct.
Oh.
So the rate of change of volume is a dv dt, yeah?
Yeah.
Is it increasing or decreasing?
Decreasing.
So is it positive or negative?
Negative.
All right, negative what?
200.
Yeah. And unit?
Cm cube per second.
That's it. That's what that phrase is telling you. Its volume V is decreasing. So the rate of change of decrease, dv dt, is negative because it's decreasing at 200 cubic centimeters per second. So dv dt is negative 200 cubic centimeters per second.
Yeah.
All right. Now, you told me earlier, what type of shape do we have here?
What type of? What?
What type of shape?
Oh, sphere.
How do we calculate the volume?
4 pi r squared.
No, that's surface area.
4 over 3 pi r something.
Okay, so cube for volume, square for area. So the volume of a sphere is 4/3 pi r cubed. Our job is to show that, dv dt is 4 pi r squared dr dt. That's the first thing we need to do. So it might be easiest for you to think of it. I mean, I've run through it one way with you to kind of explain the reasoning behind it. But in terms of working, probably just, it might be easier just to, if you understand it, that's fine. And that builds it up. But basically, you can think of it as deconstructing it to be dv dt is dv dt something, and then d something dt. As long as these two things match, it's okay. Now, it would make sense because we know v equals 4/3 pi r cubed to big R. So, kind of think of it like a fraction where it cancels. It's not really mathematically correct to think about it that way, but, maybe that'll help you remember it. And dv dr should be pretty easy. That just means derive v with respect to r. So what's that? Derive v with respect to r.
Yeah.
So what's derivative of v with respect to r?
dr dt.
No. dv dr just means to derive volume v with respect to r. So basically just think of r as the x, if you and then derive it. What's the derivative? So we know v equals 4/3 pi r cubed. So what's dv dr?
Oh, 4 pi r squared.
Right. And dr dt just stays. And that's it.
Yeah.
Are you clear on that?
Mm-hmm.
That's basically all this is.
Yeah.
All right. So then I guess we need to do the next, A, B, C now. So A, at what rate is its radius decreasing when the radius is 5? So let me rub that off and we'll just continue here for A. So A, what is it asking? At what rate is its radius decreasing? So they're saying find what?
Dr dt.
All right. So basically find dr dt when
R equals to m. 5.
when r is 5. And centimeters, like pay attention to that, but essentially when r is 5, yes?
Yeah.
All right. So then, well, we use the relationship we already have. We know dv dt equals 4 pi r squared dr dt. But we know from here that dv dt is negative 200.
Mm-hmm.
And we know from here that r is 5. So basically we've got negative 200 equals 4 pi times 5 squared times dr dt. Are you clear with that?
Yep.
Which therefore means dr dt equals negative 200 divided by 4 times 5 squared pi, which is, well, negative 2 over pi centimeters per second.
Yep.
Is that clear?
Mm-hmm.
Right. Okay. So let's do B. And by the way, Paris, you know how before you were basically saying that you wanted to sort of do sort of exam questions kind of thing?
Mm.
Yeah, so these are, I mean, they get harder and they most definitely get harder. But in an exam, these are, towards the sort of questions that they would be asking. So, we're now moving towards solving problems rather than just actually just doing derivatives, right?
Yeah.
So, in an exam, this would be a pretty standard question, but, and obviously, you've just tried it. And so you've still obviously trying to come to grips with what everything means. But, just to show you, these are textbook questions as well, right? But these are now obviously getting to the point where, where you're getting more like an exam question, right?
Yeah.
More like an exam question. All right. So B, what is the radius when the radius is decreasing at 2 pi centimeters per second? All right. So what is B asking for? Find what?
Find R
When
when dr dt equals to 2 plus positive 2. Oh, yeah, negative
what?
2 pi.
Okay. So basically in mathematical terms, B is saying find R when dr dt equals negative 2 pi. And centimeters per second is understood. Note, we already know that, dv dt equals 4 pi r squared dr dt. And we also know that this is equal to negative 200. And so now we just basically sub things in, right? We know we want to find r when this thing is negative 2 pi. So we basically have 4 pi r squared times negative 2 pi equals negative 200. And we just basically solve for r. So you can see that the 2 cancels, the negative cancels, the 2 cancels. So on the left-hand side, you'll have 4 pi squared r squared, and you're going to get 100. So that means r squared must equal 25 over pi squared. And that means your r must equal 5 over pi for r being positive. Because you can't have a negative radius, right?
Mm.
So therefore your answer is 5 over pi centimeters.
Yeah.
Is that clear?
Mm-hmm.
All right. So let's now do C. Let's now do C. So C, what would C be asking for?
DRDT.
Correct. So at what rate is the radius decreasing? So that's the RDT. When?
When volume is 36.
So basically at this point in time, let me just do it on a new sheet. We know that dBdt is 4 pi r squared times dRdt. We also know that dBdt is equal to negative 200. And the questions are saying find dRdt when V equals 36 pi. Understand?
Yeah.
Now here's the thing, we know V, right? I mean, they tell us, what V equals, yes?
Yes.
But if you look at our expression that we're relying on here, are we using V?
No.
What are we using? If you're looking at, we're not using V, but rather we're using what letters?
DRDT.
Well, we use the RDT, well, that's what we're trying to find, yeah? But what other letters do we use? There's no V in there, but what letter is there?
Pi. R.
R, right? Pi is, a letter, is a Greek letter, but more importantly, it's a constant, right? So the point is, we don't know, we know V, but that doesn't really help us, like, in a way you might feel it doesn't help us directly because we don't have a V to sub in. Does that make sense?
Yeah.
But what that does mean is we can sub in an R, yeah?
Yes.
So can you see what we would need to do firstly?
No.
We'd need to find R so that the volume is 36 pi.
Oh, yeah.
So basically the first step we would need to do is, using the relationship that V equals 4/3 pi r cubed, which is 36 pi, find R. Firstly, we would need to do that. So in other words, we're solving for 4/3 pi r cubed equals 36 pi. You can see that the pi just cancels. You can probably see that if we multiply 3 across and divide by 4, then you'll get 27. And if r cubed is 27, then that means r must equal 3. And centimeters is implied, given that everything is in centimeters right now.
Yeah.
Does that make sense?
Mm.
So basically, this is the condition they've given you directly. But essentially, this also tells you the condition that r equals 3 that you have to work out.
Yeah.
And once you've got that, then it's very similar to the questions we've done before. We've got it now r equals 3. We want to find dRdt. We know dBdt. equals 4 pi r squared times dr dt. We know dv dt is negative 200. We now have r being 3. And we just solve for dr dt. Note that it's negative. That means it's decreasing as we would expect. And note that, its unit is centimeters per second. Like your final answer should include the unit.
Yep.
Good. All right. Clear with everything?
Mm-hmm.
Good. All right. Now, rather than going through max min today, let's leave that till next week. I'll just run through another problem with you, yeah?
Yeah.
So, very similar question, but let's take a look. You've got a spherical balloon to be filled with water so that surface area increases at a constant rate of 1 square centimeter per second. So what's our shape?
Sphere.
Right. And we need to consider its surface area. So what's the surface area formula for a sphere?
4 pi r squared.
Correct. And we are told that it's to be filled with water so that its surface area increases at a constant rate of 1 square centimeter per second. What do we know?
dA dt.
I'll call it SA because I've already done SA on the left. But yeah, the unit of the surface area with respect to time is?
Positive 1 square centimeter per second.
Very good. All right, so dSA dt is positive 1 and, with the implied unit of, square centimeters per second. A asks us to find when r equals 3. So we already know when r equals 3. Find what? Part 1.
When, dSA dt.
No, we already know dSA dt is positive 1.
Oh.
Part 1 asks us to find the required rate of increase of the radius. So it wants us to find
dr dt.
Correct. It wants us to find dr dt. So let's do that first. Well, dr dt, and let's just quickly ask you for the second one. Now, instead of finding the required radius, it says the rate at which the water must be flowing in at that time. Think, for the water, if the water is flowing into the balloon, what is the water doing to the balloon? What is changing about the balloon? Specifically, that would represent how the water.
Surface area is increasing.
Well, the surface area is increasing, but is that what the water directly affects?
The volume.
Yeah. So the required rate that water must be flowing, they're asking you to find what? T?
V.
dt. Exactly. So let me run through how we do this question. So for part 1, like this is just all the interpretation, all right? So that's just to be clear as to what you would need to do. So part 1, we know that SA equals 4 pi r squared. So we know dSA dt. I'll just rewrite this information out. So, we want to find dSA dt because we know that's plus 1. So that means it's equivalent to finding dSA dr times dr dt. Now, dSA dr is just deriving surface area with respect to r, which is going to be 8 pi r times dr dt. But this is equal to 1. So dr dt must equal positive 1 over 8 pi r centimeters per second.
Yep.
Part 2, dv dt, recognize that v equals 4/3 pi r cubed. So dv dt, well, would therefore be dv dr times dr dt. And the reason we're doing this is because we know we needed to find a dv dt, right?
Yeah.
And so dv dr is just going to be 4 pi r squared times dr dt. Now, if we hadn't worked out dr dt already, we'd have to go back and work that out using, dr dt equals, dr dsa and times dsa dt, if we hadn't worked that out. But because we have already worked it out from before, under the same situation, because we've already worked it out under the same situation, we can just sub it in. That leaves us with, r over 2 in general. And that leaves us with 3 over 2 cubic centimeters per second, because r equals 3.
Yeah.
Does that make sense?
Yeah.
Great. Okay, Paris. Good. Let me know if you've got any problems with that. Work on